Please welcome Jessica Smith.
Thank you. So let's get started. So what does this function do? Anyone?
Exposes PHP to vulnerabilities.
Yes, but yep. So probably thinking it just downloads the content on that web page and then just displays it to the screen. But it actually does a lot more than that. And we'll find out what it does and exactly sort of what happens underneath, what one single function call can actually do. So about me, I've been using PHP since 1998, and I'm a senior principal engineer at DigiCert working on the DNS platforms there. I also organize LAN parties and do LAN party gaming and build networks for events that sort of look like that. It's a nice hobby. So going back to this is a really good example of abstraction. And abstraction, if you don't know, is removing unnecessary details to allow us to focus on the problem we're trying to solve. So we don't want to be distracted with all the detail that goes on underneath. We just want to get down to doing what we want to do best. So we're using this all the time in PHP. Laravel is an abstraction over having to do all the routing yourself and invoking controllers and stuff like that. Eloquent ORM as part of it, that's abstracting you away from the database. You don't have to know about writing database queries. Guzzle is an abstraction over the sort of HTTP libraries, so you don't have to use file get contents and pass in a HTTP context to it, or use all the curl functions. You can just use a simple library to do it. It hides this away from you. PHP itself is an abstraction over C and doing stuff low level. So it's abstractions all the way down. It's good. It means we don't have to worry about these things. But there is a problem with them. So way back in 2002, Joel Spolsky coined the term the law of leaky abstractions. All non-trivial abstractions to some degree are leaky. And what he means by this is that when you use an abstraction, sometimes you are so distant from what's happening underneath that problems that occur with it become difficult to troubleshoot or to find the cause of. So Eloquent ORM is a good example. You can sometimes have it producing queries which are really slow, and you don't really know why until you start looking at the SQL it generates, and there's functions to let you do that. But it might just be an index needing to be added on a database table. But unless you can actually sort of look underneath that abstraction and know what's going on, you're going to have a difficult time with it. And networking is no different. That slow query could be because of some networking issue to the database. So knowing about sort of these abstractions and what's underneath them can really help you with sort of improving things. So this function, it's many, many layers. It is literally like the iceberg meme. So traditionally, to teach networking, people will get taught the OSI model. It's 7 layers, and you start from top to bottom, and they all build upon each other, and it's abstraction over abstraction. And the top level application, that's your protocol like HTTP, and then you go down through encryption, encoding, sockets, HTTP headers, TCP, UDP, IP routing, Ethernet and ARP, and then the cables and the RJ45 connectors. And we'll go through some of that later. But the trouble with this model is it was designed back in the 1970s, and it was good for everything back then, but then TCP/IP came along, and how we use the internet today sort of came along. So it's generally better to think of it in a much more simplified model of just 4 layers. So in this one, we've got the application layer, we've got the transport layer, the network layer, and the physical layer. So we're PHP developers. We're going to start with the application layer. So these are all stuff we sort of use and we actively see. It's the stuff that's in your browser, email, games. It's the protocols we use, HTTP, SMTP, compression, encoding, and TLS and encryption is sort of in there. It merges a bit into the transport layer. But generally, this is the one we tend to work with the most. We're doing JSON encoding, decoding, sending HTTP headers and stuff like that. The next layer down, we've got protocols, TCP, UDP. We've got all the ports that you connect to and what they all mean. And we'll also probably come across this most of the time. It's pretty common for us. We also get things in there like error correction, flow control. And this is where the data starts getting split up to travel across the internet. So when you want to send data across the internet, you do have to break it up into small chunks that can be sent, packets. And the size of this is limited by what's known as the maximum transmission unit, or MTU, which is generally around 1,500 bytes, and it's a bit lower on some connections. Anything above that, it will get split up into separate packets. And that may not be what you want. So, TCP, Transmission Control Protocol. This is connection-based. It gets established with a three-way handshake. When you're talking to a server, you'll send a SYN packet, then you get SYN ACK back from there to say it's acknowledged it, and then you send an ACK back to it. And it's a three-way handshake that happens to establish a connection. It's reliable. The packets will always arrive in the correct order. Anything that's missing and isn't acknowledged will get resent. And it's got sort of 20-byte header at the start of every packet. So the way I always imagine this is if you've got two buildings next to each other with lots of windows in them, and you want to get a tennis ball from one building to another through the windows, this is like putting a massive pipe in between two specific windows and then rolling the tennis balls down the pipe. They will always arrive in the correct order, but there you can start to see a bit of a problem with it. If, tennis ball goes missing or whatever, you need to wait for it to be resent, and then that will delay things. So, it can slow things down a bit. A missing packet can cause it to be delayed. Lots of missing packets if someone's on a really slow connection or mobile, and it can start getting really slow. So, it's great, but it's got some drawbacks to it. But this is used, HTTP uses it a lot of the time, although we'll get on later to when it doesn't. SSH, SMTP, database connections, they're normally TCP because you want that reliability. In contrast, we've got UDP, User Datagram Protocol. So this is connectionless. And because it's connectionless, the packets could arrive in any order. They could go different directions through the internet. Missing packets aren't resent. So if a packet gets dropped, it's up to the application to know and reassemble it. It's got an 8-byte header, so it's smaller. There's no handshake because there's no connection, so it's quicker to establish and set up. So it's very good for real-time applications. Computer gaming is a classic example of that. If a packet gets dropped from a game server to you, it doesn't matter because it's pointless receiving it. Streaming video traditionally was like this, although HLS, which is used now sort of primarily on YouTube and Twitch and such, they've switched to TCP because they can. So that's that layer. Moving on, the network layer. So underneath that, we now have the network layer. And this, again, we'll have some interaction with. So we'll know about IP addresses. So the other part, though, is routing. And routing is something where we probably know a bit about it or have heard things, but we don't know any of the detail. And we'll get onto that. So IP addresses. IPv4. We know IPv4. It's what we're used to. 4 octets that make up an IP address. There's about 4.3 billion of them, and we've run out. We decided early on that that was a great number to have, and I think it was about 10 years ago they were all allocated. If you want to buy any more, they're about $7,000 for 256 of them. Because of this, we start to use things like network address translation. So this is where you have multiple people behind a single IP address. And some mobile companies and ISPs will use carrier-grade versions of this. So they'll have thousands of users behind a single IP address. And this is something we might want to know about if we start putting restrictions on our site based on IP address. So if we do an IP block on something, it might actually block thousands of users. So, it's something that we have to be aware of. The other IP version we've got is IPv6. So IPv6 tends to scare people because it's not the sort of 4 numbers they're used to. It's a massive hexadecimal value. It's 128 bits. There's 340 undecillion, a lot. There's more than we'll ever need. And as it says there, last year, 45% of all the internet traffic was IPv6. Hopefully there's more websites now using it, but 30% is not bad, but it's been around since 1998. So adoption is a bit slow. Most people's home networks aren't IPv6. A lot of ISPs in the UK still don't push it out. So it's there. But again, for us, we may find that interesting because if we want to do IP blocks, someone who's got IPv6 will have hundreds of thousands, millions of IP addresses they could use. So we maybe need to start blocking networks or that kind of thing. Or if we're storing IP addresses, if we're storing them, we can no longer store them in sort of 15-byte values in a database because they just won't fit. So IPv6, it's a different form of IP. It's worth knowing it's there. Use it if you can. But IP addresses are good, but they're not memorable, which is where DNS comes in. So DNS is, traditional example everyone gives is it's like a phone book for the internet. You look up the name in the phone book, you find the address that it relates to. It can do a bit more. You can specify different network services. So there's SRV records, which can specify, for example, where a SIP service, so a sort of telephony service is. There's various things like you can specify which certificate authority that you want to use for your domain. So you can say, don't trust certificates unless they're issued by DigiCert. It's useful for things like that. It can be used as part of validation. If you're using Let's Encrypt, you can use DNS validation and it will create a text record to identify the domain. So, that's other uses of DNS. And it works as a hierarchy of records. You have the root of DNS, which is the .domain, and that's served up from root servers around the world. And then they will know where all the other domains underneath it are. So they want to know where to go for UK, where to go for com, where to go for net. And then you can query those, and they'll tell you where to go for co.uk or Microsoft.com or something. And then underneath that will go down. You query .co.uk, and you'll get PHP conference.co.uk, and it'll tell you where that is. And it's a massive hierarchy going all the way down. It's such an important part of the internet. And when it goes wrong, it really goes wrong, and you see it everywhere. Last year, Cloudflare DNS went down for an hour, and it was big news. Keeping DNS online, there's lots of interesting stuff around how that's done. Because if you think about it, if you're using Cloudflare DNS at 1.1.1.1, how is that available everywhere? How do they keep that up and available everywhere? The answer to that is routing. So routing is basically how do we get from one point on the internet to another? There's lots of different types. The main one on your home network or you'll come across on your laptop or anything like that will be static routing. So if you use Tailscale or you VPN, it will add routes into a routing table on your PC, and it will say, for this network, go to this IP address and use that as the place you go to get to it. Everything else, send to your router. And that's, what we're used to. But then you've got various dynamic routing protocols. And the main one on the internet is one called BGP, and we'll go through that later. And to make things easier for routing, we group IP addresses together in blocks. So these blocks are known as subnets or networks or prefixes. And you generally can denote them using a subnet mask, or you can denote them using the slash notation there, CRDR notation. So the example I give there, 44.30.69.0 to 44.30.69.255 is known as a /24. And from .64 to 127 is a /26. So how do we work that out? What does this actually mean? So if we look at our network here, so we've got our IP address of 44.30.69.42. Our starting IP for our range is .0. Our ending IP is .127. Our subnet mask is 255.255.255.128. And if we were to actually write that down in binary, you would see that it would be a sequence of ones and then zeros. And there's 25 significant bytes there, ones. And that's how we get to the slash notation. So that's how we can kind of group IP addresses together. And that's useful because when we're starting to route things around the internet, with 4.3 billion IP addresses, we can't have routing tables with 4.3 billion entries. It takes up a lot of memory, routers won't handle it. So we group things down into small chunks to the point where the smallest actual routable chunk on the public internet is a /24 of 255 IP addresses. So I mentioned static routing. If you do the netstat -n command, I think, on macOS and iproot on Linux, you'll see a routing table, something along the lines of this. It will specify the network, and it will specify the gateway for that particular network range. At the bottom there, 0.0.0.0/0 is your default route, and that specifies where anything that isn't elsewhere in the table goes to. And routing will always prefer a more specific route. So A /24 is more specific than a /0. That /25 is more specific than a /24. So it will always pick the most specific route to get to the destination from a static routing table. The other form of routing, which is used on the internet, is BGP, or Border Gateway Protocol. So the internet really actually is a series of networks. These are known as autonomous systems, and there are thousands of them all connected together. They're all represented by a number. Mine is 204776. And when the networks connect to each other, they literally announce, I can provide access to these network ranges. Use me if you want to get there. And it will also list the networks that it will send the data through to get there. So what this looks like on a routing table. So say we are there and we want to get to our destination over there, which we know is on AS600. AS200, which is us, we can see that routes we've got, we can either go 200, 300, 500, 600 to get there, or 200 or 400 to 600 to get there. So, yeah, one of those is shorter than the other, and generally it will go that way and it will take the shortest path there, but not always. It might be that it's cheaper to send data to 300 than it is to 400, and it will make a business decision to go, actually, yeah, we're going to send it to 300. Or it could be that it knows that the link to 300 is sort of a slower link. Maybe they know that it's a lot slower, so they definitely won't use it, but they've got it as a backup just in case. So it will generally take the shortest route to get there, but not always. So what happens when a network goes down? Because we all know that the internet is supposed to be this reliable thing. In the case of nuclear war, it would stay up. That was its original creation. So the great thing about this is when you stop receiving the announcements from it, you stop having that route as a path to get there. So now there's no choice. It has to go 300, 500, 600 because that one drops. And this generally takes place in less than 30 seconds. You can tune it and make it even quicker. But yeah, this is how we adapt to sort of routers dropping offline and networks going offline. So in the beginning, in the intro to the talk, it was mentioned about anycast. So because you've got all these announcements and you're announcing you can get to this IP network through me, what you can do is in different geographic locations, you can announce the same network ranges. And this is actually how all the big DNS providers work. Cloudflare DNS, Google DNS, everyone at scale doing DNS does it this way. In London, we announce that you can get to 1110/24 directly from us because we've got stuff in a data center in London. We do the same in Frankfurt. We have a data center, we say, yeah, come to us through here. And based on where you are, you'll generally take the shortest route to get there. So in the UK, if you were to go to the one in Frankfurt, it would be 4 different ASs to go through. But if you were to go to the London one, it's only 2. Likewise, if you're in Germany, it would only be 2 to go to the one in Germany. And the great thing about this with DNS is not only is it redundant, because if that link to London goes down, it will still go to Frankfurt. But it also means that you can serve up different DNS records based on where they are. So if the customer is coming from the UK, you can then decide, okay, we're going to block you accessing it because we're Imager and that's what we do now. And Imager's block is entirely DNS-based, which is why just VPNing won't necessarily fix it. But it's great for fault tolerance and it's great for that kind of geo-redundancy, and that gets used a lot in DNS. But also mistakes can happen. So I mentioned earlier on, it's sometimes when stuff goes wrong, it's DNS and outages. The other thing that can go wrong is BGP routing. And sometimes BGP causes DNS problems. So in our example here, what happens if some malicious entity or just someone by accident announces that actually you can get to 443069/24 through me, and you can't? Well, depending on how it's configured, the AS200 will just go, yeah, all right, you're a shorter route. You're one hop. Yeah, I send it to you. And yeah, this when it's done accidentally, it's a BGP leak. And yeah, network operators who link together, they generally have mailing lists and collaborations on this. And if it happens, you get mocked, and then, you'll fix it. When it happens maliciously, and it has been in the past, it's known as BGP hijacking. And there are some mechanisms in place to start kind of proving security over who's allowed to announce what IP address is. But about 60% of it is still based on trust and literal letters that are shown. So you end up with a letter of intent that you show and say, yes, I'm allowed to announce this IP range. And everyone else goes, oh, okay, that's fine. Right, so now we get down to the physical layer. So the physical layer underneath, this is literally the exact connection itself. So anything from 5G, Wi-Fi, satellite, low Earth orbit satellite constellations like Starlink, network cables. And the main thing we're concerned about there as developers is the latency and the quality of the connection. So if someone's on a mobile connection, it's probably not going to be that high quality. If they're on a mobile connection, it's probably low latency. The other thing with physical is the limit there's the speed of light. Stuff that is further away does take a lot longer. It's sort of 30, 40 milliseconds to the US. It's getting on for 200 milliseconds over to Asia and sort of Australia. So that matters for us because we generally want to host content close to our users. If people are using our services, we want things to be responsive. The further away we are from them, the slower things will be. We don't want to serve stuff up from the US East if all our customers are in Germany. Likewise, though, this also matters for us with connections to databases and APIs we use. If we're constantly using an API from someone, we want to make sure that it might actually be more preferable for us to put our content closer to where we're pulling it from the API. Because if we're making 10 API calls for every request the user's making, it makes more sense for it to make it slightly slower for the user than to have that extra round trip time on every request. So that's why it's worth it for us to sort of know about this. And in terms of knowing about the user's connection and what they've got, there are ways you can determine this. You can look at the user agent on the browser and work it out from there. Or you can even use services like GeoIP lookup services like MaxMinds, which will also tell you what they believe the connection will be. So on an incoming request, you can then go, okay, this connection is a mobile device. Okay, it may be slightly different. And you might want to vary behavior in your application based on it. You can also take this a bit further. So none of the layers above care about the layer below. You don't have to care about what connection is being used, what physical medium is being used. You don't, if you're just writing a PHP application and serving it, actually care about the web server and how it's serving it. It's the web server. It runs your application, it returns it. You don't know how it's actually doing that, how it's getting to the user. You just know it is. So at one extreme, there is an RFC for IP over AV and carriers. Literally writing out or printing out the data and tying it to a pigeon's leg and sending it. Written as an April Fool's joke back in 1990. And it's been done. In 2001, the Bergen Linux user group actually did it. And that's the literal ping request that they produced from it. There's other fun ones like IP over bongo drums. I'm hearing muttering about packet loss. Yeah, they sent 9 packets and they only got 4. The RFC is a good read. It's full of lots of jokes. But IP over bongo drums is another one that people have used, and it's sometimes used in teaching labs as well in university courses. So we've got our function call here, file get contents, and it's an iceberg. So let's see what actually now goes through when we do this. So the first thing we actually have to do is we have to do a DNS lookup, because ip.mintopia.net is great, but it's not the actual IP address we need to connect to. So we'll do an IP address lookup. So we use DNS for this. DNS is traditionally UDP, but if it's a really large response, it will say switch to TCP and get it through TCP. Or you can also have it served over TLS using DNS over TLS or DNS over HTTPS if you're concerned about OPSEC. That's traditionally. And we use DNS because it's quick. We want these responses really quickly. We don't want to be delaying. And DNS also has lots of caching built into it at every layer. So it will get cached locally. It gets cached at your ISP's name servers. It'll get cached further up. And we generally want to use DNS servers located close to us. So we want to be using sort of a big provider's anycast DNS services. So using Cloudflare's or Google's. If you're hosted in a single location, using one for your ISP, your host may be better as well. So once we've done the DNS lookup, we've now got the application layer, and we're using HTTP. What version of HTTP are we going to use? HTTP 1, old, don't want to use it. HTTP 2, still in use quite a lot. HTTP 3, more recent version, built on Quick. We'll get into some of that. But yeah, we're going to be using HTTP because it's web page stuff. And we'll get into more of HTTP 3 in the next layer, which is transport. So I said before, TCP is traditionally used for HTTP, but a few years ago, started using UDP for it with HTTP 3. So HTTP 3 enforces TLS. It's UDP. It doesn't have a handshake, so it's quicker to establish. It doesn't have as much of the acknowledgements, so it can be slightly quicker to actually use. It's got mechanisms built in, so if packets do go missing, they get retried. HTTP 2 also has their own TCP. It's got some stuff as well around. So if you're downloading multiple files at once or things and packets get lost and it delays it, HTTP 2 does have something to help with that, with downloading multiple things at once, but it's not ideal. It's still TCP. UDP, doesn't matter. It gets lost, we'll just resend it. We'll carry on in the meantime downloading stuff until that gets resent. So this is really good if the user's on mobile and they're switching from 4G to Wi-Fi. Because if you're using TCP, where it's a connection between two things, and they switch connection types, that's going to drop if they switch from Wi-Fi to 4G. If it's UDP and it's connectionless, it's not. It's just going to pick up any packets which were lost while they switched over, will just be resent. So HTTP 3 is brilliant and is probably how we want to do things now. So the network, IPv4 or IPv6, we don't really care. But we might care in our own application, as we mentioned before. We might care if they're using NAT. We might care if we're storing the IP addresses. We also don't overly care about the routing. The routing of it is kind of secondary to us. But we sometimes might want to actually be in a position where we can host the content closer to the users. Now, if you're using a globally distributed database or you're not using a database, you might want to actually look at either hosting stuff closer to the users normally, or even using anycast. Many CDN providers now actually support anycast. So they will put your content in data centers, it'll just be accessed through anycast, and it will always come from the data center closest to the user. So that's something to be aware of. And we go on to physical. The main thing we care about on this is going to be that distance. So making this request to this API, we're going to want to ideally be close to that API. So, yeah. As a bit of a summary, abstractions are leaky. Knowing what happens underneath an abstraction really helps. It's how we get better at doing things. Use HTTP 3 where possible. It is just better in every single way. It'll be better for your users. It's better for us. Stuff like franking PHP with Caddy supports it. You do need to use TLS, but again, franking PHP and Caddy will do auto TLS for you. So it's really easy to do. And if you're using sort of third-party hosting, make sure that they also support it because it will be better for you. And the main thing is locate the applications as close to other services or users as you can. If your users are in the UK, host it in the UK. If they're in Germany, host it in Germany. If you're serving something globally, have consideration about globally distributing it and serving it out from lots of places. There's even stuff you can run PHP in Lambdas and AWS if you want to. There's a few projects about like Ref, which will do that. So you can really sort of globally distribute it if you need to get it close to users. And yeah, it's always DNS. Unless it's BGP. And unfortunately, my job, sometimes it's both. Yeah, that's a quick run through of networking. So, any questions on networking? Feel free to drop in the Slack or read them out. Or yeah.